and enriching his knowledge with MTech from IIT Kharagpur. Sir brings to our department a wealth of practical wisdom, having dedicated a decades to the industries from 1992 to 2002. His extensive teaching experience spans over 20 years, making him a formidable authority in the fields of electrical machine, power electronics, and drives. As we welcome Professor Debashis Chatterjee, sir, he anticipates a continued legacy of excellence and innovation in electrical engineering education and research at Jadavpur University. Now, I request Professor Debashis Chatterjee, sir, to kindly enlighten us. Sir, please.
So, first of all, thank you all, and a very good afternoon or evening, rather, coming to all the delegates and the participants and the organizing committee. And it's really a pleasure that I really thank the organizing committee for arranging such, say, FDPs on topics which are really relevant, and not only relevant now, it will be relevant, continue to be relevant by another next 20 years at least, because everything is going a paradigm shift, not only the generation, not also the loads and etc. So therefore, it will be a very interesting, I think it was a very interesting, maybe this is the last lecture for this FDP. It was a very interesting outcome probably for all the participants, and getting a chance to react, or rather interact with different academicians from different part of the world. So thank you again. So then I'm starting the lecture now. We'll start from little bit basics and then find out. Our main aim is to find out the areas of research and grow some interest in the people, so that more and more people come to research regarding e-mobility and you can say renewable generation, etc. So therefore, let us hope that we can do something for you also. So I will go for PowerPoint or a PDF, which I think PDF I will try first.
Okay, sir.
See, is it visible?
No, sir. Now it is visible, sir.
Visible, na?
Yes,
And pages are changing.
yes, sir.
So this is a better one actually. Sometimes this this PowerPoint does not change the pages. So that is why I have converted the file to PDF. And let us start from here. If you have no problem, so this side I will continue. I think all participants are comfortable with this, na?
I think so, sir.
Okay, all right. So the topic what we have really chosen is like this: that electric vehicle, the recent trends and modern control techniques, right? So we will discuss a little bit of background, why we go for this kind of research or this kind of applications, and then slowly we will move into the technological areas. Now, if you see here, first of all, people will tell you that why electric vehicles? Everything is there. I mean, and the vehicles are running very comfortably with fossil fuels. So why do we go for electric vehicles, right? So if you see really the background, first of all, you see where do we get our electricity? Now, this will give a little bit of idea regarding the electricity generation till date. Maybe a little bit of 1 or 2% here and there, a little old data. Here is maybe 2010 or 2011 data. So here we see that till now, the majority of electrical power generation is from coal, around 50%. Then comes natural gas, right? And petroleum, 3%. So if you add both these three, you get 75%, around 75%, right? 75% is dependent on fossil fuels. And again, nuclear also, it is a directly not fossil fuel, but it is also a reserve in the earth crust, right? So then another 20% if you add, then it is around 90% or more than that, right? So the main danger is actually that these fuels may be exhausted, first of all. Secondly, even if it is not exhausted, the method what we apply these days, all of you know actually, that generates a lot of toxic gases, or you can say greenhouse gases, toxic as well as greenhouse gases in the environment, which are responsible for many catastrophic things, right? So therefore, the two ways we are trying that to have a paradigm shift of, generation of electricity, right? Say maybe avoiding those fossil fuels and do something which is actually green energy, first of all. Uh, Secondly, if you just look at the effect of the effect of the fossil fuels, this is, as we have said, greenhouse gas, and majority is CO2, right? Majority is CO2, and CO2 emissions actually it is recorded for say from 1800 to 2004, say like that 200 years, 200 years. So it is growing and growing exponentially. And that thing is still, even if you plot up to 2020, the scenario will never change. It will be even stiffer, right? Then the thing is that forget about this per capita and all. Then this ppm wise, how much it is increasing? If you see around 2 ppm per year or 0.5% per year, it is really alarming on an average. So actually, why it is so? Now, this plot will give you why it is so. Here we see a little bit of more expanded version, like say from 1000 AD to 2020 or 2000 AD, like that. Now you find here that uh, that till 1769, the CO2 emission in ppm was almost more or less constant and hovering around 280 ppm, right? But just after 1769, there is a steep rise, even more than exponential, you can say. Eh. Then what is the reason? The reason is written on the top, which is actually on 1769 in this year, James Watt took patent for the steam engine. That means the modern civilization began to rotate, and we tried to use coal as a fuel for the steam engines, right? And then the thing really changed. So therefore, actually, to save the world, people or we different scientists, they are really trying that how to avoid the usage of this kind of fossil fuels, which are really responsible to emit such gases and then have some adverse effect on the atmosphere. Right? Then again, if you look at the greenhouse gas emission data on, say, this is a 2017 data on Indian Governmental Panel on Climate Change. So you will find that there are several areas which is really responsible for greenhouse gas emission. Say the major areas are energy industries in 28%, energy industries 28%, and then comes transportation 23%, right? So then naturally the focus can go on transportation sector, really, how to remove that or how to stop this greenhouse gas emission, right? Then people thought of different ideas regarding electric vehicles and so. But still, I'm telling you, electric vehicles is actually broadly, if you see, the vehicles run by electrical source. So source should be mobile. So usually batteries are used. Now again, if you charge the battery from conventional sources, right, whatever available in the grid, so again it becomes of no use. So only by running electric vehicle will not really help unless and until the charging stations, which are actually responsible to charge the battery, that are run or that are fueled by renewable sources. Otherwise, the purpose will not be served. So there should be two steps. One is that electric vehicle introduction or electric vehicle, more research on electric vehicle and all those things. And second, the charging the batteries from the renewable sources, right? So these two should be the mottos. Now the history, if you see, the electric concept of electric vehicles are not very new. They are very old. Now you see here some years are noted where 1837, then 1884, then 1890, battery run cars were really available, right? Battery run cars were really available. Again here the batteries, if you see, since the battery is more important because it is the energy source for the vehicular motors, then battery was a really research area. And if you see here, that research also started in 1830s or in 1800 AD. So therefore you find that there were initially non-chargeable batteries, and then 1859 chargeable batteries came. Then again 1859 to 1890 deployment of electrical powered drums, and then 1990s, say another 100 years, right? Lithium ion batteries, right? So these are the real development which are actually taking place on batteries. And here also, if you find a little bit more expanded historical development of electric vehicles, where you find that electric vehicles were conceptualized even these years, 1860 and all, right? And then 1912 and all those things. And nowadays, in 1990s and onwards, actually, this technology came more into you can say commercialization, and then people tried to adopt, simply because you see, some of you, I don't know, maybe many of you are juniors. If you remember earlier books or and so this the electric vehicular technology really dependent on two three things. One is that electric motor, that is okay. Then another is the driving mechanism, right? The other one is the battery, and then battery charging. So now, when the driving mechanism and battery chargings are concerned, they are more actually more rely on actually these power electronics based developments, like say devices, as well as the controllers, the VLSI chips, which are really those DSPs, digital signal processors, etc. And in 1970s only, thyristors came for the development of power electronic circuitry or power electronic applications, right? After 1970s, all those devices slowly came, power BJT, and then IGBTs, MOSFETs, power MOSFETs, and nowadays you have silicon carbides, right? So wide bandgap devices, etc. So now, then actually the actual development, and again you see that microprocessor or microcontroller wise, that digital signal processing and all. So from 2000s onwards, actually you find a lot of such things are coming. Like say nowadays you have Raspberry Pi and a few other things, ATMega and all, which are really easily available, programmable with high memory and high computational capability, etc. And even a first year students, even they are not even engineers, they can run or they can fly those yeah, what is that? Run robots or fly drones, which having with precise control, right? So therefore, availability of these devices and the controllers and control mechanisms, they have made it possible. Otherwise, it was not possible before that, right? And then, of course, battery technology is improving. of course. So then even the people knew it long back, but they could not apply it, right? So now the technology trend, if you see here, we are actually really trying for cutting edge research on zero carbon emission electric vehicles. Zero carbon emission. That means we don't want any entirely electric, right? Now, EVs are divided, if you see, they are into three basic categories. One is known as BEV, battery electric vehicles. I mean, they are run with batteries, and then battery can be charged inside that onboard charging or offboard charging. And then second one is actually plug-in hybrid electric vehicles, PHEV, BEV, PHEV, plug-in hybrid electric. Now, hybrid electric is actually, they are, I'll show you all the configurations slowly. They are actually run both by gasoline, or you can say, I have indicated as gasoline, or you can say petrol, as well as the electric, both. And there are various configurations. So hybrid electric vehicles are a little bit costlier, but they are more reliable these days because we are slowly shifting. So there must be some in between, right? So electrical equipments are really prone to failures because of this power electronics, okay, and the devices, and it can fail instantly, right? So therefore, some thing like say hybridization along with those conventional IC engines and all, that makes it a little bit safer. So then it is known as PHEV, plug-in hybrid electric vehicles. And third one is FCEV, fuel cell electric vehicle. It is similar to battery, but it is powered by fuel cell, and they are actually for very large vehicles, and they are costly, and they are not used that much, commercialized that much because of their large cost, mainly for very big transportation systems. They are tried. So then if you see here, the configuration, the first one is actually the conventional, pure gasoline, or you can say pure petrol engine. Now here we have a petrol engine, a transmitter, and a transmission system rather, and a drive shaft to the wheels, right? It is simple, which we are actually having these days around 99% of the cars, for the 99% of the cars. Second one is actually pure electrical, we have said BEV, battery electric vehicle, as we have said, pure electrical, where we have a battery and then an electric motor. Then it is indicated as motor stroke generator. Why? I'll just tell you. And then similar drive shaft, right? And then wheels. Now this motor stroke generator means actually in electrical system or in mechanical system, if you see, often, very often here for the vehicular system, very often they are accelerated and braked, if you see the road conditions, due to road conditions. So now when they're braked, what is happening? The kinetic energy, whatever is there inside in the vehicle, in that mass of the vehicle, you can say, that has to be really dissipated somewhere in terms of heat in the brake and etc. Right? And because it is an electrical system, we can have some arrangement that we can drive this motor as a generator and bring back those kinetic energy back to electrical and recharge the battery. So that is why this is known as regenerative action, right? That is why it is M stroke G, right? Now, coming to the actual configuration now, how they will be configured. Now, this is actually a battery electric vehicle, BEV. BEVs are configured this way, BEVs are configured this way. Now, this BEV, if you see, we can have a central battery, right? We can have a central battery, and we can have EM means electric motors. So here G is not given. You can assume that all the motors can be converted as a generator with the help of the drive system. That is why we have a arrow both end. Here going energy, it is the power flow. Power is going to the motor, and it can coming back. It can also come back from the motor to the battery. right? That is the generating axle. So we can have a configuration where the front wheels have individual motors, right? And the back wheels are having a central motor with a differential axle, right? Well, a mechanical differential you can have. So this can be a one configuration. And the second configuration can be actually, we can have individual motors to all the wheels, right? And the differential action for the motors, that can be taken care of by individual drive system, right? Make electronic differential system can be employed, rather deployed here, right? So battery will act as a central source, and each individual motors that can be fitted into the wheels, and it can be driven, BEV configuration. And the third one can be actually, it's a differential on both sides, and single electric motors on each differentials. That means two electric motors will be there, and then it will have a mechanical differential for both the wheel pairs. So these are actually the configurations which are really deployed for the BEVs by different companies, right? And we'll discuss a little bit which companies and what some whatever information we have. Now then come the hybrid electric vehicle, HEV, plug-in hybrid electric vehicle, PHEV or HEV, whatever way, right? So then here, this PHEV, if you see here, we have both, right? We have a gasoline engine here, and we have a electric motor here, and they are coupled on the same shaft, and that shaft power is having a transmission system to the wheels. Now the battery is interacting with the electric motors, and a gasoline engine definitely will interact with the fuels, fuel injection systems, etc. And there will be a control system. So you can have the flexibility to drive the car or drive the vehicle either by this electric or by gasoline or by both. Maybe some peak torque deployment can be done with this gasoline engine, right? That different ways. So this that will be decided by this control system, and a lot of research has been really going on this topic. So then, if you come to the actual configuration as per the individual motors and etc., so let us concentrate on this one, HEV or PHEV, whatever way. We can have an IC engine here, fuel, and then this IC engine is driving a generator, right? This generator is actually developing electrical power for the inverter stroke rectifier combination and electric motor. That means it is run in electrical, but actually the electrical power is generated by the IC engine, right? So then the question of say combining both of them goes a little bit simplified, and we can have an alternate source of battery, right? Then the battery can be charged from outside, or it can be charged by this generator through this inverter. That's why this both end arrow is there, and we can have a transmission here, and only front wheel or only back wheel drive is there. So this configuration is really popular, and it is a you can say reliable also, because if sometimes battery power goes, so then IC engine can be started and the electric motor can be driven. Now once the electric motor gets faulty, then here everything is gone, or the inverter is faulty, then everything is gone. But the power source problem is actually from both this, either through the IC engine and generator, or through the batteries, right? So then next configuration, if you see, is also quite interesting. To remove that problem, the second configuration here, that says that the IC engine has a direct coupling with the transmission. It is a series actually, although it is series, but it is shown like this. So IC engine has a direct coupling with the mechanical system along with the electric motor. They're series. Okay, it can be separately driven. Now this battery is individually driving this electric motor through this three-phase inverter rectifier combination. Of course, here rectifier will not be required, only inverter combination, right? So it's a general statement, so that has been given here. So here, that portion is gone. Even this inverter fails, or the electric motor fails, or the battery power goes. So in both the cases, IC engine can drive it individually. Or even when there is a requirement, say it's a very rising a very high slope, so we are needing a very high torque demand. So the IC engine also can be started with the help of the control system to supply that peak torque demand, right? So this is a very popular configuration also, and it is used in many of the companies or many of the electric vehicle manufacturers. Now the third combination, this is the you can say this is the costliest combination for the hybrid electric engine or hybrid electric vehicle. Here the IC engine, you see, it is having both the facilities. Like it can have a direct coupling with the electric motor, right, in series, as well as it can drive a generator. It can drive a generator, right? It can be coupled with a generator. So then, even if it can be driven in two modes, either it can supply power through generator and this rectifier inverter to the electric motor, or it can directly supply. And then battery also having as a source. Battery is also being a source that can also be, I mean, used to drive this electric motor. It is the safest one. I mean, here failure is almost, I mean, you can say negligible, and is a highly reliable one, because this IC engine, they are I mean highly reliable, and it can participate in generating electrical power as well as mechanical power directly. Yeah. Okay. So these are the three combinations for hybrid electric vehicles. So I am not going to the fuel cell. Fuel cell is nothing but you replace this battery with the help of a fuel cell, and rest things are similar. And this is not widely used because of its cost and space requirements and all other safety requirements, etc., etc. Because hydrogen fuel cells, hydrogen is combustible, as well as it has got other hazards also, storing hydrogen, etc. So therefore, there are comparisons. So I'm not going to exact comparison. I will only show you popularity, that which one is actually used which ways. So it is shown from 2011 to 2020 worldwide. Actually, it is not for India. Global shipment. Now, if you see here, PHEVs, they are actually lower compared to BEVs. BEVs are the major part, as I have said. And then FCVs are coming up, but they're very, very small compared to other two, right? So PHEV, BEVs, they are used in different ratings, different classes, and then we'll discuss which one is where and how to use them. So this is the, I mean, scenario for development. And then you see here that electric vehicles, as we have said, that they are not something new to the world, and the core element for the batteries are, for the electric vehicles are batteries, motors, and then you can say battery charging units, then motor control units, etc. So we will discuss that what kind of motors, what kind of characteristics we need, how to achieve that characteristics, what are the electronics involved, etc. So now the motor characteristics, if you see first, it should have a characteristics like to have a high starting torque. As you know, that electric vehicles dead weight is high. So if you search any site, any vehicle, say 100 k, sorry, 1000 kg, Even a bike weighs 150 kg or 200 kg like that these days. So uh, therefore, actually, and along with there will be some say 5 passengers or 4 passengers, whichever way. So therefore, it is likely to start with load always because all the passengers will ride and then the motor will start. Okay. So therefore, first requirement should be that it should have a very high starting torque, right? Secondly, it should not take a very high space, big space, because then the vehicular size and all other things will be little bit make it discomfortable or rather uncomfortable. Now, this is taken care of by this high power density design of the motors, high power density or high torque to weight ratio of the motors, and then good efficiency. Now, efficiency, if you see good efficiency, as we have said, it is utilizing the battery power in most of the cases, apart from that hybrid vehicles where we can have other. But the thing is that since the battery is charged from sources, renewable and all, so maximum usage is our really motto. But the another way to have this good efficiency criteria or high efficiency criteria, another to think is that if you see a low efficient motor, let us say a motor having 60% efficiency and another motor having 95% efficiency. So now this 60%, then 40% power is lost, right? Lost where? It is lost in terms of some active power losses, like say core loss, copper loss, friction loss, and all these losses develop heat inside the machine. So more losses means more heat and lesser life expectancy of the motor. So making a design of highly efficient does not mean that you are saving energy as well as you are saving the failures also, right? So therefore, good efficiency criteria is really a inevitable characteristics for such motors. Now, we will discuss about some few motor characteristics and how we electronically achieve them, right? Now, motor characteristics, if you see, it can be categorized into usually two types. One is known as soft characteristics or series characteristics. Now, here you see that the starting torque is really high because at speed equal to 0, you see torque is really high. Practically, it is theoretically it is showing infinity, but usually it is not so. But you can assume it to be a very high torque at starting, right? And why it is soft, that is to be understood. Just I will discuss the hard characteristics next, and then I will show you. Now here the second one is actually stiff characteristics, or it is known as the shunt characteristics because it is the characteristics of DC shunt motors, you see. Now here you see at speed 0, here also torque is high, but the thing is that the characteristics is not really suitable for vehicular application or any traction application. Why? Now come back to the earlier one. Come back to the earlier one. Now here, you see here that say this is the operating point. I think that arrow mark is seen by you. Okay. So say this is the operating point, right? Now you imagine a drive system having some wheels. Now the wheels are actually their diameter, outer diameter changes depends on air pressure within the wheels, isn't it? Within the wheel tube, or nowadays it's tubeless, whichever way. So that overall diameter of the wheel actually that can shift a few millimeters, say maybe 0 to 4-5 millimeters like that. Okay. So now you are to drive the machine or you are to drive the car or the vehicle at a particular linear speed, right? Say 60 kilometers per hour, right? It's a linear speed. So now for a lower dia wheel, right? that rotation will be more for same linear speed, because omega r, v equal to omega into r. So if r reduces for same v linear velocity, omega has to increase. So now here you see, when speed increases, that by some small amount, right? Small amount, the torque change is very small. Say at the operating zone, at the middle, okay? Torque change is very small. So that is why it is known as soft characteristics. Now, if you look at this here, stiff characteristics, for a small speed change, the torque change is very large. Then what is the effect? Effect is that you require more power. You require more power, or rather more torque, for lower speeds, right? So that may not be possible for all these motors. So that is why every motor, whichever used in traction, they are actually of this series characteristics. Even if they are not having that characteristics, the electrical controllers which are driving the motors, they make the characteristics like series characteristics. Okay. So then let us come to the type of motors that are usually used for traction application. Okay. The first one is actually, I will go for full screen. Full screen is okay, na? The screen size is okay. Hello. The
Yes,
screen
sir.
size. Okay. The screen size is okay, na? Okay. So the types of motor, if you see, the first one is a DC series motor, as we have said. We started with the series characteristics. The second one is brushless DC motor. Third one is permanent magnet synchronous motor, or it is known as PMSM. Fourth one is three-phase AC induction motors. And the fifth one is switched reluctance motors. So these are the 5 categories of motors that can be used as a drive system, as a part of the drive system for the electric vehicle application. Now, if you look at the first one, DC series motor, they were widely used in locos, electric locos traction systems. But for small cars or smaller applications, like say electric cars, either, or even 2-wheelers, 3-wheelers, etc., they're not really suitable. Although they are having a very high torque capability. Now, it was really useful in the olden era, as you have said. It is written here in 1900s, etc. Yeah. In 20th century or like that, simply because that it was very easy to control, even with rheostatic control. And then nowadays we are having good controllers, electronic controllers available, and those drawbacks, whatever there, has become really weighty these days. Oh, that is why we don't go for DC series motors, because of their brass and commutator requirement. They require frequent maintenance, as well as they cannot be used in all environments, like say dusty or even ionic environment, or in case of very high humid conditions. So there can be a risk of short circuiting the commutators, etc. So although it is the best motor to run, but it is not used. And also equivalent cost, rather cost of equivalent rating of DC series motors are more compared to other categories of motors, whatever we have shown these days. Right. So that's why it is written here. See, main drawback is brushes and commutators. And although the railway is used, they have almost shifted to 3-phase induction motors. But small vehicles, it is not really used. Now, the useful motor is actually this one, brushless DC motor. Now, it is similar to DC motor with permanent magnets. But the thing is that here the commutation is achieved. Commutation means changeover of current from one line to another line, or rather you can say, if you assume so many phases in the DC armature, so one phase to other, right? So this in normal brushed DC motor, it was achieved with the help of commutator and brush, mechanical commutation, right? Now here, brushless DC motor, we have electronic commutations. That means the currents are electronically shifted from one coil to the another coil, right? And that is why the drawbacks are removed, characteristics is remaining, and then we can use it. And we have a permanent magnet instead of field, electrical field, whatever, instead of say electromagnetic field, what we had that in DC motors. So that reduces that reduces the losses in the BLDC machine and increases the efficiency. So we can find an efficiency to the tune of 95 to 98% for the motors rating around, say, 250 watt to 4 kilowatt or 3.5 kilowatt, like that. Depends on design. And not only that, that high density permanent magnets have also been developed nowadays. So therefore, the manufacturing has also become easy, and you can say cost has also come down, because of the rare earth magnets, they are also coming, already come. And then we have high torque to weight ratio, as we are saying, because that's what high density design and all these things. And these motors are most preferred motors for electric vehicle applications due to its traction characteristics, cost, high torque to weight ratio, efficiency, lightweight, everything, whatever you can see. Okay, but the thing is that their design for high wattage is little bit restricted because of the permanent magnet action and this commutating torque, commutation torque level problems, etc. So they are mostly designed within a range of, say, 5 kilowatt or so. Above that, the design is normal, right? So it's not really available. So they are low wattage. Now, if you see the types, so types of BLDC motors, there are two types. One is known as outrunner type BLDC motor, right? And they are known as hub motors. Outrunner means outer portion is the rotor and inner portion is the fixed portion, right? And they are fitted in the wheels, right? And the wheels are the motors. And in the middle of the wheel, we have the shaft coupled, and outer thing runs. Okay, so that is why it is known as outrunner type and hub motors, right? And does not require the external gear, as we have said, because it is directly the wheels. They are the motors. Wheels are the motors for the vehicles, right? Now these motors are less bulky and does not require any gear system. Repeatedly I am saying. And then space requirement, as we have said, is very less. They are used mostly in electric cycle and scooter applications. Electric cycle and scooter applications. So all the electric scooters, if you find here, so this picture I am showing you, this is the BLDC hub motor picture. This all the electric scooters, and they are actually hub motors. So you will be really familiar with this kind of figure, where any electric scooter you see the wheels, you will find this one. So BLDC hub motor, very popular. So no transmission required. So transmission efficiency is also saved. Everything is saved. Okay. So now here, if you look at the inner construction for the outer rotor machine, so it is like this. So inside we have coils, right? And the rotor is having permanent magnets. This red ones, blue ones, they are north pole, south pole, etc. And the stampings are shown, inside which there will be windings. So windings can be shifted and run. So windings currents can be shifted and run like that. So Then come the other category, which is known as in-runner type. In-runner type, where it's a normal motor, means you have a rotor which is inside and stator is outside, right? And stator is outside, and then external transmission is required. In this kind of system, or in this for this kind of motor, you require some transmitter arrangement. Okay, maybe a belt drive, maybe a chain drive, etc. And naturally, this will be bulkier, and these motors are of higher wattage. Higher wattage. So these hub motors they are not above 1 kilowatt or 1.2 kilowatt. These motors can go up to 4 to 4.5 kilowatt, as I have said. Okay, so these are actually in-runner type motors. And three-wheelers, many of the three-wheelers and low and medium performance scooters, they are employing this, right? And electric vehicle applications. Now here, the main drawback is high cost due to permanent magnet, and overloading of the motors beyond certain limit may reduce or really reduces, you can say, the permanent magnet characteristics. Because if you see, due to retentivity, the actually charging and discharging path, rather you can say that BH curve, if you see, they do not return through the same path. So therefore, losses as well as whenever it is a high loading. So when you come back, actually the demagnetization, whatever has taken place, that can remain. That can remain. I mean, the full magnetization will not be retained actually. So that is what is there. And here also you have two types. One is inner rotor machines, inner rotor, rather interior permanent magnet machines, where we have the permanent magnets inside the rotor, and exterior permanent magnet, where we have outside the rotor. Okay, in exterior rotor, by mistake I have not given any picture, right? And then interior permanent magnet, the permanent magnet are inside. Okay, usually this interior permanent magnet is used because for high speed applications, the to reduce say losses, friction and windage losses, inner rotor machines are I mean interior permanent magnets are more suitable. So that is why probably I have not given. So this is the typical picture. This is a typical picture for the this type of machine. And then this is a transmitting system, power transmitting arrangement. So this is the wheel, and then this is the motor, and there are two sets of belt drives has been shown here. Maybe there are different companies or different ratios may require different arrangements, but this is a typical one, as I have said. I think that some of the electric scooters, like say Hero Vida and all, they are utilizing this kind of system. Maybe they are using with PMSM or BLDC sometimes, but the transmitting arrangement is this. This is actually inner rotor machines, right? So then the third one is actually permanent magnet synchronous motor, PMSM. Now PMSM, it is actually, if you look at the cross-sectional views and etc., they will be a little bit similar with the BLDC motor. But the arrangement is such, here also permanent magnet and armature winding is there, but the arrangement is such, the windings are distributed windings. Means here we have a sinusoidal back EMF pattern. But in case of BLDC motor, they are concentrated windings and trapezoidal back EMF pattern, right? So these are the differences. And permanent magnet synchronous machines, PMSMs, since they are sinusoidal, so they can be designed or they can be run at high power ratings also. Means even any synchronous machine, they can run even 10 kilowatts, 20 kilowatts, 25 kilowatts, whichever way. So design can be made for high wattage ratings easily. So they are mostly used for high power machines, buses, then trucks, you can say that big vehicles, you can say, This is the PMSM back EMF. This is the trapezoidal back EMF. You know this. Since it's a discussion, so we have included everything. So we will go slowly inside. Now, the permanent magnet synchronous machines, as I have said, they are of higher ratings, right? PMSMs are the best choice for high performance applications like cars and buses. More precise speed control can be done, and they are a little bit more costlier compared to this BLDC machine or so of equivalent rating. And then it is having stiff competition to and compared to induction machine, you can say, because induction machines are rugged and they don't require any those such permanent magnet arrangement and so, and they are demagnetized and everything is not there, but still PMSM is providing a very stiff competition because it's having very high efficiency, high torque to weight ratio, and all those things are there. And therefore, this is widely used in case of electric vehicle applications. And PMSM, sometimes it is costlier than BLDC motors. And then we have given some examples like, say, Chevrolet, and then Ford, and some other Nissan, BMW. They are also doing a lot of research on, they have already, launched their vehicles on PMSM motors for propulsion or for transportation application. Okay, so then this is the inside view for the PMSM. Okay, that anything you can see. The fourth one, because time is running away, maybe 6:30 I will end up. This three-phase AC induction motors. This is actually this is the so far the best choice as per the ruggedness, best choice as per the ruggedness and cost. You see, if you remember, these cage type machines are, they are having cages in the rotor, and their maintenance is almost negligible, right? And their cost is also lowest among all these motors, whatever we have discussed so far. These motors having some drawback, not to have very high starting torque like DC series motors, but we can have the controllers which can make it high starting torque application. So like say BYF applications, if you remember, for at a lower voltage, lower frequency, we can start it at high torque, right? So therefore, the characteristics like series motors, high starting torque, and then soft characteristics, everything can be achieved with the help of three-phase AC induction motors, and it is giving a steep competition to all other motors, you can say. And majority of the manufacturers, vehicle manufacturers, they are also trying or undergoing a lot of research to implement their system with induction motor, because failure is very less compared to others. Only drawback here is its efficiency. Its efficiency is around maximum 90 to 95%, 95%. Whereas with PMSM or BLDC, we can achieve more than that. 96, 97% is easily achievable for high rating motors. But if you take care of, or if you consider the drive system along with the motor, because overall efficiency will be the multiplication of the drive efficiency as well as and the motor efficiency. So here the drive efficiency can be made little bit higher compared to PMSM drives. And there are techniques. All these things we cannot be discussed here. But anyway, there are a lot of research going on ultimately to improve the drive efficiencies also, you can say. So those who are interested, they can search papers on this. Okay. So this is one. And these are the picture is, not too much of interest. Now, permanent magnet motors. Now, the thing is, if you see here, that, and here no question of demagnetization will come. Its performance will almost remain same throughout its life. Okay. Now, adjusting B and all, this is okay. Motor characteristics is okay. I just skip few things. Then this BYF we'll see later. Now here, which one uses induction motor? If you see Mahindra Reva, actually, though it is discontinued these days, some other motors are coming. Tata Motors and TVS, they are using induction motors in few cases. Okay, Tata Motors are really using induction motor in their cars, but TVS for some applications they will be also using induction motors for its propulsion. Okay, so then induction motors are the preferred choice for the performance-oriented electric vehicles. Now we will see how the performance can be improved. Now, rugged environmental conditions, they can be used. Due to these advantages, Indian Railways has started replacing. So that's what I have already spoken. So these few slides I will skip. Now I will go to this motor. This is also very interesting. Switch reluctance motor. Now here, I think I will show the construction first. Here, this construction is like this. We can have, this is the rotor portion. This is the rotor portion, okay? Middle one. So interestingly, it is having some salient nature and no other windings in there. It's a solid rotor, right? And then there is no winding, no magnet, nothing, no demagnetization. And the stator is having coils, right? So it is, say, 1, 2, 3, 4, 5, 6, 4 by 6. So 4 stator, you can say, 4 rotor poles, you can say. Actually, they are not poles, but poles, and then 6 stator windings. So 4 by 6 machine it is said. Now, by shifting these pulses, or shifting the currents from one phase to another, one stage phase to another, the magnetic field can be rotated, and this rotor actually can be made an induced magnet, and it will rotate in synchronism. So this is the technique of rotation. And here you see, since the rotor is having no magnet, no winding, this is one of the most efficient motors. Here you can also achieve an efficiency around 97-98%, and then precise control is also achievable. Although at high rating, you can say this is not a very popular drive system till date. Lot of research, lot of drawbacks are there regarding the sensorless drive systems, its parameter optimizations or parameter determinations, and then smooth control, because it is shifted from this to that. So here some torque pulsations can arrive at low speeds. So these are having some few drawbacks, but you have a lot of research scope on this drive, this switch reluctance motor drive, so that it can be applied for vehicular application. It is simplest in construction so far, and then you can say efficiency is very high. And since the rotor is having no winding, it is low weight, so it can achieve very high acceleration. I mean, in a very short time, pick up what we say in terms of our language. Then high speed application is also possible. High power density is also possible. But thing is that only that speed fluctuation, or you can say torque ripple, is its major drawbacks. And since the rotor is having no winding, so it is easier to cool the motor also. Cooling is also not a very issue here. It has also issue of some noises, as we have said. Noise issue means torque ripple. From there, some noise issues are there. So, I mean, anybody is interested, they can start doing research on this machine and do something for electric vehicle development and all. Okay, so this is what for the motors. And now some thumb rules we will see how to select motors, which motors to select where, and for the drive system, right? Now, selection, if you see, it depends on few things, like say, first of all, operating conditions and the cost and the rating, right? Now, here, a thumb rule is that if the thing is that you are doing it for a two-wheeler application, and where really cost is a major thing. If you see two electric scooters, one is having a cost 2,000 rupees less, people will really go for it, right? Now, low cost system, and it does not require, I mean, for low speed scooters, it does not require very high performance also, right? So the choice is mostly or only, you can say, the BLDC hub motors. Now, for a second case, for three-wheelers or two-wheelers, without an external gear, if you don't want an external gear, don't have a space to mount external gear, so naturally here also hub motors will be helpful. Now, where we have a space, you can use that BLDC in-runner type motors, a little bit higher rating, say 4 kilowatt, 3 kilowatt, like that. And for all other higher power applications, the choice is between two motors till date, which is either PMSM or induction motors. Now, they are, say, 9,900, like that, their weightage. Somebody can do everything with PMSM, somebody can do everything with induction motor, right? So there are, I mean, those who are strong on research on PMSM, they are applying PMSM. Those who are strong research induction motors, they are applying induction motors. And there are a lot of development on PMSM also is going on during high starting torque development, motor-wise. So few of the startup companies, they are really interested in developing more efficient and more suitable PMSM motors for vehicular applications, right? So their opportunities are there. So now, motor-wise, we are almost, almost gisted. We have almost gisted everything, right? What can be used where, and what are the motors they are used, what are the characteristics they are really required, and then their applications, etc. So now let us come to the electric vehicle as a whole, as such, what is there inside it, and how to design, develop everything, right? So now here we have given a pictorial view. These are the four wheels, right? Four wheels, and the transmission system is given. And then we have an electric motors here, EM written, although it is an induction motor probably. And then induction motor is driven by a three-phase inverter, right? Now, research can be done on this inverter also for efficient operation, right? Now, the inverter is powered by an high voltage DC bus. This HV DC bus, high voltage doesn't mean very kilovolt, few kilovolts, right? High voltage here is actually according to the rating of the motor. Normally, maximum 415 volt motors are used, right? Maximum. For some applications, it may be lower voltage, 200 volt motors, 220 volt motors are also can be used. Now, this voltage is actually the high voltage in case of EV application. 400 volt bus, right? Or 200 volt DC bus, like that. Because here, the battery voltage is 12 volt, so that is low voltage. Now, with respect to 12 volt, 200 or 400 is high voltage. So that is why it is written high voltage DC bus. So now this high voltage DC bus is powered by two things here. One is DC-DC converter, which has an input from supercapacitor, right? And another one is actually from a propulsion battery, as we are discussing that time, battery, right? Battery powered vehicles, battery. Now they're parallel, right? Parallelly operating and feeding DC bus. Now, how the battery is powered? Battery can be powered in two ways or charged in two ways. One is onboard charger. Onboard charger means which is actually within the vehicle. We can have only the grid connection directly coming to the vehicle plug. right? These are plug-in vehicles, plug-in electric vehicles, right? So onboard chargers. Or off-board means actually the charger is outside. Now here we can have a off-board charger which is outside. Battery also can be taken out and charged and then fitted here. There are provisions that can be done, right? Now here you see why this is powered by this high EV-DC bus. One is supercapacitor, one is propulsion battery. Actually, these batteries nowadays also, a majority of the batteries are lead acid, and then comes the lithium-ion batteries, or then other batteries are coming. If time permits, or the other part of the lecture is there in some other day, I will discuss those portions, right? So then these batteries do not have an infinite charge discharge rate limit. Like say, as we were discussing in the beginning, sudden requirement of some torque, say sudden slope, right? Or on the other hand, suddenly the machine is braked. Now the power has to be absorbed by the battery very quickly. So the battery will not be able to do it, right? So in that case, actually, this supercapacitor is used. They are used for, say, you can say a stopgap application, like say sudden requirement that can be supplied by this, and sudden absorption, very fast absorption of power that can be also uh, applied by this. Now, these capacitors are having high energy density, low voltage, high capacitor values, 2-volt, 3-volt capacitors. Naturally, the boosting of this should be either by 2-3 stages or by some high gain boost converters, So this is also one developmental area that has been coming. And then power sharing actually between these two. This is actually non-isolated system. They are directly coupled. Okay, so there can be isolated systems that we will discuss sometime. So then this power exchange, or you can say power sharing also is an issue, you can say, till date. So there can be some failures regarding this power sharing failure and all. So this is there. So this is supercapacitor is for the emergency case. That means high sudden requirement or sudden absorption requirement, like that. Then another thing is coming here, you see. One is again low voltage DC, LVDC to DC, auxiliary battery. Now what does it do? Now this LVDC is of the order of lower voltages, like say 30 volt, 20, 24 volt, maximum 48 volt, like that. This is to supply auxiliary powers, like say horn, light, and your sound system, like that. So this is auxiliary power that will be supplied by this battery with the help of this low voltage DC bus. And then high voltage DC bus will actually supply this three-phase inverter to drive the motor. So this is the overall power electronics or overall architecture. Now the research can be done on any of this, like say this fast charging converter, or can be this onboard charging technique, or this power sharing, or this high high gain DC to DC, or this inverter, like that, motor even, right? So there are scopes. So this is similar picture. I am not going to do. Now one thing is that we have seen that DC to DC converters are used in 3 places: for the low voltage case, and for the supercapacitor case, and for the high voltage battery, high voltage bus from the battery case, right? So there are different classes of, time will not permit me to discuss everything, but you know many things, but still as a part of the lecture I am covering. So DC-DC converters for BEVs and PHEVs, they are of these categories. They are majorly isolated or non-isolated. The green ones are usually suitable for BEVs and PHEVs, like say interleaved, multi-port, bridge, Z source, SHBC like that, then full bridge, up bridge is not usually used, then boost, right? Because of several advantages, disadvantages are there, so we are not going to discuss. Now, few of the converters, basic topologies, we will discuss, and then we will go for the motor control applications for this lecture. If time, I don't know, I think here only we will be ending. So here we will discuss a few pros and cons regarding these converters, say widely used converters. So DC to DC boost converter, this is the configuration you all know. Now here the main drawback is that although it is a boost, it is written, it cannot be used to boost it for more than 400% because of the stability problems and all other issues, oscillations and all. So moderate gain only possible up to 400%. That means if your input voltage is 1 volt, you can maximum get around 4 volt there at the output, right? And the efficiency is also very moderate, as you see that all these converters, they are used there, and definitely if they are not efficient, naturally overall efficiency of the system will be decreased, because battery is having some power, right? Now it is supplying to the DC bus to the DC-DC converter. Now DC bus is again supplying to the machine through inverter, and then machine is again driving. So at least 3 such efficiencies are coming, and overall efficiency is multiplication of all these 3. Now here it is only 85% to maximum. So this is not a very helpful one. Okay. And only advantage is that here cost is lower. Okay? So drawbacks, it is already discussed here. So I will not go back. I will not go here. Now here a little bit modification of this is this interleaved DC to DC converter. Interleaved means you see here that a single converter configuration is multiplied into 4 and they are switched alternately. And the basic advantage is that all these converters, all these devices, Q1, Q2, Q3, Q4, their switching frequency is reduced by 1/4, right? Naturally, the devices, I mean, the converter efficiency is highly affected by losses inside the devices. 2 losses, one is switching, one is conduction. So switching losses are really one of the major part. So overall total loss that can be reduced, and this filter sizes can be reduced, and this type of system can be used up to maximum of 30 kilowatt rating, as I said, and efficiency of around 92%. A little bit better efficiency is achievable, as is said here. So as there it was showing 85% or something like that, and with the help of this interleaving, we can increase a little bit more, and 30 kilowatt rating, simply because the current is also divided by the 4 devices, so we can have higher ratings. Okay. Now the third one is actually the full bridge boost DC to DC. Here the boosting is done, but the technology is a little bit different with the help of a high frequency transformer coupling. This is the isolated one, isolated supply. Now from the battery we can have high frequency switching of these devices, Q1, Q2, Q3, Q4, and then this ferrite high frequency transformers, these are rectified, and then this is also achievable for a little bit high power of 30 kilowatt. Efficiency is still around 92%. Right? Then isolated ZVS converter. Now ZVS, as you know, it's a soft switching technology. All those are hard switching. ZVS is 0 voltage switching. That means at the time of switching on, a condition that a voltage across the device is 0 is achieved. So then, since power loss is actually V into I, if V is 0, so switching power loss will be 0. So ideally, but usually due to different reasons, I mean, deviation of operating conditions, and then L, C, shifting, etc., etc. So this is not a very highly reliable design for high kilowatt. Is usually designed for less than 10 kilowatt system. Its efficiency is a little bit better. You can have an efficiency of 93-94%. Actually, not suitable for high power applications. Now this one is really developing these days. You can keep on searching the varieties of this, or and do some research. And this is a multi-port arrangement. Earlier in the vehicular architecture, we have shown it isolated, non-isolated one. Actually, the DC bus was there for coupling between the supercapacitor and the battery. Here, actually, a transformer coupled application is there, and you can have several such batteries, and then or several such capacitors that can be coupled. And power sharing issues are the issues that can be that are still some problem that can be solved. And then this converter, you can say this can be achieved for bidirectional application also, from battery end to motor, and then rotor to battery, everything. And this is a widely applied application, and its efficiency also ranges between say 90 to 94%. And you can have some, download some papers and see it. And they are future, you can say, variety of these are future of this power DC to DC converter system for vehicular applications. Now, this is some, you can say, bidirectional application, non-isolated, as we have said there. And how the capacitor is working, it's not moving. Just a minute. How the capacitor is working, just we have taken some from some of our research. Sorry, some problem with yes. Arey bapre. Just a minute, the slides have shifted. This is the problem for the online system. Just I will show you that, as we are saying that how the supercapacitor power is actually supplementing during requirements. Say we have taken two cases. Say one power requirement is there. So this is the battery power. Sudden decrease in DC bus power. The battery increase is slow, right? Now this is supercapacitor. Whenever a requirement, high requirement is there, it can increase the current instantly. And when it is achieved, then the current, when the torque is achieved, the current slowly it can come down, right? Similarly, while absorbing also, braking, now the battery power is slowly absorbing, you can say, and then here you see that supercapacitor takes that current very fast, right? And then after stabilization is achieved, it is actually restored back to the original current. So this way actually the supercapacitor operates, right? And then the other variants are multi-device interleaved. Multi-device means here it's a fail-safe operation. We can say fault ride-through operation, we can say. How? Now see that the same boosting is actually achieved with Q1, Q2 and Q3, Q4, right? And from the second one, LB, it is actually Q5, Q6, Q7, Q8. Now initially Q1, Q2 and Q5, Q6 will be operative, right? If there is any failure, there will be semiconductor fuses that will isolate it, and instead of that, Q3, Q4 will operate. so that even if one leg goes, it will operate. So this way actually, and then it is non-isolated, and then this supercapacitor and battery both are coupled, positive end at the here and negative end here. So this way also, there are a lot of variations. I am telling you, a lot of research. You will find hundreds of papers on this, interleaved bidirectional converters. Now we will see something. I think here we end because it is 6:30, 6:27 now. So maybe there is another part of lecture coming in the next week. Maybe I will be more comfortable there, because if we discuss very fast, I don't think anything you will be able to assimilate. So if you have some questions, please come forward. So I end up here
Thank you,
for
sir.
this day.
Thank you for your valuable lecture. And our dear participant,
So participants, if you have some questions, please come forward so we can discuss and see whether we can.
call for.
Sir, why we are not using the normal synchronous motor instead of permanent magnet synchronous motor?
Oh, normal synchronous motor. See, normal synchronous motor require one more excitation, right? Rotor excitation, DC excitation. So that will make the thing bulkier, and rotor loss will increase, because overall efficiency will decrease. If you supply power to the rotor, so rotor copper loss also will come, and then you have to make another arrangement. Motor will be heavier, bulkier, costlier, everything is there. So, and the requirement is such that your design is up to 30-35 kilowatt, major motors, maximum. So it can be easily designed with permanent magnet. So that is why it is not given. For requirement of efficiency, mainly efficiency and space.
Okay, thank you, sir.
Any participants? Any other participants? You can
So,
write.
thank you very much. So I'm stopping the presentation. Okay.
Okay, sir.
Okay. You just tell me.
Okay, sir. I think there are no questions.
No more queries. That means
No
whether
queries.
either they have understood everything or nothing. So anyway, hopefully, so my earnest request is that I would like to see
Sir,
few of you at least coming to vehicular research area.
sir,
And then
one question in chat box.
what is that chat box? You please spell out. Better
Why
don't
are
write.
BLDC motors not used for high power applications?
See, there are some design problems. There are some design problems for high power applications. Now, those permanent magnets and trapezoidal EMF. Now, trapezoidal EMF, if you apply for high power, so it has got very high harmonics. So overall drive system, that commutation from one phase to another phase, will be really a problematic one. So they are not designed. They are not designed for high power actually. So that is the reason.
Oh, no questions, sir. Okay. Thank you, sir. Thank you for your this lecture. So we will meet again shortly, I think 7:30 during validatory session.
Today, right.
Okay,
Okay.
sir. Thank you, sir.
Thank you. So I'm leaving it now.
Okay,
Okay.
sir.
Okay.